In this session, we introduce electrochlorination, the on-site generation of sodium hypochlorite from salt, water, and electricity. We will review the basic electrolysis process, required raw materials, product quality, and key operating and alarm functions for safe, reliable disinfection. This diagram shows undivided cell electrolysis. A brine solution flows between negative and positive electrodes. When DC power is applied, chlorine and hydrogen gases are produced and react with the brine to form a dilute sodium hypochlorite solution, typically 0.5 to 0.7%, which is safer to store and handle. Here we see typical product analysis for a 0.6% chlorine solution. The table lists measured chlorine, chloride, chlorite, and chlorate levels. Note that chlorate must remain below 5.4% of available chlorine, as defined in EN 901, 2013, to ensure compliance for drinking water applications. Salt quality is critical. The feed salt should be free from silt and have low levels of calcium, magnesium, and heavy metals. Bromide content must be very low when treating drinking water to avoid formation of unwanted brominated byproducts during electrochlorination. Water must be of near potable quality, with low turbidity and iron. A reliable supply is essential, as high residual chlorine can damage softener resin over time. To produce 1 kilogram of chlorine, we typically require 5 kilowatt-hours of power, 3.5 kilograms of salt, and about 166 liters of water. This slide frames our discussion on how salt, water, energy, temperature, and byproducts interact. We will examine how conductivity affects DC power behavior, and how adjusting brine concentration or generation time influences efficiency, product strength, and formation of secondary species. The controller uses 3 LED indicators. A green LED confirms the system is healthy and operating normally. An amber LED signals a warning, such as an alarm delay or softener cartridge change. A red LED indicates a latched fault. The system has shut down and requires operator intervention. Service menu items. 4. Manage basic timing. End program exits to manual inhibit. Restart delay defines how long the system waits before restarting after reaching tank stop level. Stop delay supports direct dosing applications, and alarm delay sets how long an alarm may persist before shutdown. Parameters 5 to 8 protect the electrolyzer and support logging. Voltage high and voltage low define acceptable DC voltage limits, helping detect scaling, salinity changes, or power faults. Clock settings ensure accurate time-stamped fault logs. The brine timer regulates brine dosing per batch. Parameters 9 to 12 configure water softening and brine metering. The softener filter setting selects the softening method. Water hardness is entered in mg per liter to size regeneration. The engineer's menu is password protected, and brine pulses define flow meter pulses per volume of brine. Parameters 13 to 16 control batch operation and ventilation safety. Water brine sets the dilution ratio. Startup cycles ensure the electrolyzer is filled before power is applied. Cycle time determines batch frequency and output rate. The airflow. Low alarm shuts the system down if ventilation drops. Parameters 17 to 20. Interface with external equipment. External tank, high and low, monitor remote storage levels. Auxiliary alarm allows an external fault input. The current sensor option enables monitoring of DC current via a transducer, improving protection against abnormal operating conditions. Parameters 21 to 24. Add further safety and control. The airflow sensor input works with airflow scaling to verify ventilation. Bund flood detects liquid in the bunded area. Remote inhibit allows external start-stop control. Scaling amps sets the correct current range. Consult Lutz-Jesco for values. Parameters 25 to 28 complete the configuration. Scaling airflow defines the airflow measurement range. Modbus address and modem Modbus select the communication settings for telemetry, airflow. High alarm sets the upper airflow limit, typically 5 to 10% above normal operating flow. High voltage alarms indicate the DC pack is increasing voltage to maintain current. Typical causes include exhausted salt or weak brine, scaling from softener failure or poor salt quality, a leaking water solenoid valve, or high resistance in the DC circuit due to loose or corroded terminals. Low voltage alarms occur when the DC pack reduces voltage to limit current. Likely causes are overly strong brine in the electrolyzer, a leaking brine solenoid valve, failure of the DC supply or relay, or internal damage or short circuit within the electrolyzer cell assembly. Airflow alarms protect against hydrogen accumulation. Low airflow may result from blocked ducting, blower failure, sensor faults, or flooding of the electrolyzer compartment. High airflow can indicate duct breaches, door or seal damage, or sensor malfunction. Each condition must be investigated. A bund flood alarm, where fitted, signals liquid collecting in the containment sump. This may be due to leaks from pipes or fittings, or a faulty salt saturator top-up or level control valve. Prompt inspection prevents environmental contamination and protects surrounding equipment. Hydrogen sensor alarms indicate gas detected above the hyperlyzer, typically below 25% of the lower explosive limit. Causes include damaged ventilation pipework or sensor wiring issues. Enclosure door alarms show the electrolyzer door is open or incorrectly refitted, or wiring is faulty. Panel temperature alarms protect electronic components. If internal air temperature exceeds 50 degrees Celsius, check for blocked or dirty fan grills, failed cooling fans, or excessive ambient room temperature. Maintaining adequate cooling is essential for long-term system reliability.